In the largest survey of its kind, the Dark Energy Spectroscopic Instrument, or DESI, mapped the baryon acoustic oscillations of over 14 million galaxies and quasars across 11 billion years of cosmic history. Baryon acoustic oscillations are regular, periodic fluctuations in the density of the visible baryonic matter of the universe. For decades, the standard model of cosmology has relied on a rigid assumption. The dark energy equation of state, denoted by the letter W, is a flat, unchanging constant. Specifically, the math requires this baseline to sit exactly at -1. This graph plots that assumed baseline against actual DESI data. The present value sits noticeably higher, between -0.85 and -0.70, while its past behavior dips below that line. Notice the specific intersection near a redshift of 0.5. Cosmologists call this the phantom crossing. Crossing this exact threshold creates a severe tension in physics. Standard single-field models strictly forbid dark energy from moving through -1. To make the math work, you have to propose highly speculative phantom phenomena to explain the data. These phantom solutions require exotic field content, including the introduction of ghost fields equipped with negative kinetic energy. Mode identity theory, or MIT, offers a completely different framework. Under MIT, the cosmological constant is not a free variable, but a surface mode rigidly fixed by the bounded topology of the universe itself. Because this constant is tied to the physical geometry of the universe, it cannot evolve over time. If it did, the entire framework would face a direct structural contradiction. We are left with a direct conflict between the varying equation of state observed by DESI and a constant dictated by physical geometry. The phantom crossing is not a physical reality of the universe. It's a mathematical illusion generated entirely by applying wrong templates to the observational data. MIT operates on anti-periodic boundary conditions. This specific geometry emits a massive cosmic standing wave that dictates the expansion history. This diagram illustrates that standing wave. A full cycle takes roughly 33 billion years to complete. Our present epoch sits exactly here, at 5.22 radians, placing us 2.8 billion years before the cycle's geometric turnaround. This massive standing wave modulates the dark energy sector, ultimately modifying the standard Friedmann equation with a periodic surface mode term. The cosmic wave acts exclusively on this dark energy component, leaving the physical expansion of matter and radiation entirely untouched. Look at this cosmic microwave background map. At the early epoch of recombination, shown here, the wave's contribution to the energy density is roughly 4 parts in 10 billion, rendering it virtually invisible to observation. By the time we reach low redshifts, where dark energy dominates, the modulation becomes prominent. The static topology naturally generates a dynamic-looking expansion history, preserving the signatures of baryon acoustic oscillations and supernovae without altering the vacuum energy itself. To understand how this dictates expansion, we calculate MIT's effective equation of state using Friedmann inversion. The resulting formula includes a correction term strictly positive at all times. As the curve is drawn, this graph plots MIT's effective dark energy over redshift. Because of that positive term, the smooth curve firmly remains above the -1 boundary. Under mode identity theory, the dark energy of the universe never actually goes phantom. However, cosmologists measure and fit the equation of state using the CPL template. The CPL template is a standard linear mathematical model approximating dark energy evolution over time. The mathematical conflict arises here. Observers are forcing this straight CPL template onto MIT's fundamentally curved, cosine-shaped expansion history. Because the linear form cannot bend to capture the cosine shape, the template is mathematically forced to tilt. This artificial tilt pushes the present-day intercept above -1 and drags the historical values down below it. The linear fit artificially breaks the boundary right here, occurring exactly at the modulation zero crossing of redshift 0.663. When this rigid linear template interacts with the natural scatter of cosmic data, the phantom crossing inevitably emerges in the final reports. The phantom crossing does not exist in the actual expansion history of the universe. It is strictly a mathematically induced artifact caused by fitting a curve with a straight line. We can test this geometric theory against hard observational data by combining the DESI bow measurements with the Pantheon Plus supernova compilation. We evaluate MIT directly against standard lambda CDM using locked parameters and identical parameter counts. As the specific values are highlighted, this table compares the resulting fits. MIT achieves a superior fit over lambda CDM, driven by a better match to the baryon acoustic oscillation data and producing an AIC improvement of -2.1. AIC stands for Akaike Information Criterion, a statistical metric used to compare how well different models fit the same dataset. When the amplitude of the standing wave is allowed to float as a parameter, the combined datasets actively request the presence of the modulation, improving the score even further. We also have to account for the tension surrounding the Planck-calibrated CMB ruler, an essential metric derived from pristine early universe measurements made by this satellite, as the markers lock into position. This graphic plots their performance against the Planck center measurement. MIT drastically reduces the cosmological tension, sitting just 0.6 sigma off the center, while lambda CDM lags further out at a 1.4 sigma drift. Adding a geometric wave accurately maps the universe's actual expansion better than a flat constant, validating the model mathematically without conjuring a single new particle. A robust scientific theory must risk being proven wrong. MIT has done exactly that by registering blind predictions on Zenodo ahead of the Euclid Data Release 1, expected in October 2026. This illustrates the primary falsification threshold. If Euclid's high-precision observations strictly prefer a perfectly linear equation of state without any curvature, as seen on the left, the phase modulation signature is disproven, and MIT is falsified. A secondary prediction states that the actual matter expansion will remain directly proportional to the Hubble parameter, proving that the vacuum energy remains completely stable. This secures the core achievement of mode identity theory. The cosmological constant remains exactly what standard physics requires it to be, a fixed property of the vacuum. Phantom fields and negative kinetic energy are unnecessary ghosts, conjured only by the limitations of our mathematical tools. The universe is not breaking its own rules. Our straight-line templates simply fail to capture its true shape. The apparent evolution of dark energy is merely the shifting position of our own epoch along a massive cosmic structure. The cosmological constant is not evolving. What is evolving is our perspective, riding a 33 billion-year standing wave through static topological space.